Yo, what's up, everybody? Welcome back. Today we are working on writing a GPU driver because we feel like it. So I guess the context is a little bit that we've been trying to explore this idea of what if we were to make a graphics card, right? And in order to do that, I think it makes sense to understand what like a sane GPU design is. In order to do that, we have to understand like this like full graphic stack, right? So we're on Linux, and we kind of know that like somewhere we write some like open GL, right? And like you write like shaders, and like you upload vertices, and you call like draw arrays and stuff. And like what happens there? Well, we know that there's this like thing called like Mesa, and Mesa is like an open source OpenGL and Vulkan implementation, and we know that Mesa has like drivers for different devices, and then we know that like kind of like below Mesa is like the kernel, right? We know that like in order like for Mesa to talk to a GPU, he has to go through the Linux kernel in some way. We know that like the kernel must talk to like, you know, some like PCI bus, and like the PCI bus has like a GPU on it, and like somehow like these guys talk to each other in some way, shape, or form. And so like what's really like not clear here is this stuff could map very closely to the stuff down here, or it could go through like many translation layers here, here, and here before like anything actually before like what actually happens at the bottom, right? And so if in the future we want to make a GPU for fun, I think it makes sense to kind of understand like this whole chunk of crap, right? So that we can decide what's like a good sane GPU design. And so that's why we've been working on writing a GPU driver, right? We are currently on this like in this section where you can do a lot of like just render to the screen without like any like advanced APIs. You can kind of like cut like this out and kind of focus on like this part of the stack. Now you won't have like the APIs for like 3D acceleration, but if we're just like, hey, I want to like draw something to the screen, this is where we're sitting. So we have written this like demo application that does this on a GPU that is not ours, right? So if I run this command, I do see, I think if I go to the right spot here, hold on. I think it's here. I'm supposed to see a yellow smiley face here. I'm not, but I promise you it works sometimes. Hold on, let's try running our virtual machine again from scratch. It might be that we have not implemented our program very well. So let's just try again real quick. One sec. I didn't want that. How do I get out of that? Thank you. And we look here. Okay. UDHCPC-IENP 0S3. Okay, let's try it one more time. No? I swear, like literally, like just before the stream started, I tested this and it worked. So I've done something wrong. But we have this like test case where we can like draw a smiley face to the screen, and we are trying to implement a driver that does the equivalent thing, but it's ours, right? So if I run the same app for ourselves, instead of showing nothing when it's supposed to show a smiley face, it kind of like fails early. That's because we have not implemented the whole driver yet. So that is the task for today, is trying to continue on working with this thing. So the kernel mode setting is what this like draw to a frame buffer type of driver interface is called. And it's something that like all of like the major Linux kernel GPU drivers will support. And this is like kind of like their flow, is that they have this like GPU buffer that they make with some like metadata attached to it, such as like its width and height and color info. Attached to like a plane where I'm a little hazy on what plane is, but I think it's like if you have like a YUV color buffer, your like Y and your UV might kind of like sit in different spots, and so you can kind of like connect multiple frame buffers to one plane. Then there's like a CRTC, which stands for cathode ray tube controller, i.e. monitor controller, which basically says like, how am I going to send the stuff that's in your buffer? Like how is that supposed to be packaged up for your display? Like things like what resolution is my display at, and what resolution is like, what refresh rate is it, and stuff like that. The encoder says like, I'm going to take the stuff that you told me to send over to the monitor, and I'm going to like put it on the wire in some format, and then the connector is like which monitor is physically connected. And between, you know, with that whole pipeline, you have like everything you need to draw a thing to the screen, theoretically. So we've been implementing that. We've been slowly working through it. And if we go into, I guess probably I want to go like this and do nvim and cd to the Linux kernel location, we can kind of show you what we've been working on. So I had some stuff commented out here, but basically we have been registering with the DRM subsystem, i.e. Direct Rendering Manager, I think is what it's called. And basically all we do right now is we say, hey, I have a connector, I have a encoder, and we are trying to move on to the next stage, which are CRTCs. Yeah. So I think that's where we're at. And I think the plan for today is just kind of keep on moving. So what we have been doing is we have been kind of implementing a virtual GPU alongside this thing. So for things like if we are asking, hey, is a monitor connected? What we do is we actually read from a PCI device that we've been implementing, and we say like, hey, if we get this specific address at this like register on that device, then we say we're connected, otherwise not. So that's kind of like the flow of what we're going to be doing. Is we're going to be kind of like moving on both sides of this thing, just trying to get like an image written to the file system. That's kind of the goal. It's kind of the goal. DRM planes is something different. If you have multiplayer image format, the frame buffer will contain multiple gem buffers. Oh, my bad. Then the plane is, I don't understand what the plane is at all yet. I think I did at some point and I have forgotten. But that is okay. That's okay. Okay. So it is 06:35 and it is time to actually write some code. So let's, I accidentally had some stuff commented out here. So I kind of want to get it into the state where we had it at the end of last stream, where we had an encoder that was not hooked up to a CRTC. And then we will kind of just follow the errors there in both our application and the kernel driver to try to figure out what to do next. So let's rebuild our kernel. We have made some improvements in Happy Hour for kernel compilation speed. Look at that. We compile our thing as a kernel module now, and our little run script injects that kernel module into a RAM disk and automatically loads it now. So it should be faster. I think we run our like test app here. He says no encoder. Right, I think this is where we were at the end of last stream, where we have an encoder. If we look at the like get resources structure, so like the first call, let's maybe pull up, maybe we'll pull up the source code to our little test app. One sec. Hero Dev, thanks for the raid. Hello, everybody. Long-time YouTube VOD viewer here for the first time, catching you live. Hey, man, glad to have you. Okay, so let's look at our little test app. What is he doing? We need to go to the right spot. So what is it, test app? So he calls like, hey, could you tell me what resources you have associated with you? As then let me find like a connector that has a monitor plugged in. From there, we can kind of figure out what the resolution of that thing should be. Then we can like create some buffers and stuff. And then I want to know like how to encode information for this monitor. And this step is saying like, hey, we are not getting an encoder, right? He says here, no encoder. However, one of the first things that we do is we ask for all available resources. And if we look at those available resources, we should see that we have an encoder here. So we have one encoder, and here is his address, right? So that's a little confusing. If we have encoders, why does he say there's no encoder? Well, how do we pick? I think that we just call get encoder ID for this connector. So the connector here, which we have logged, here, says that he has one encoder associated with him, and here's where they live, and he's looking at this encoder ID 0. And when we call this here, he's not doing what we expect. You're returning no encoder when you're trying to get a CRTC. Oh, that's a really good point. So maybe we were just confused. Thank you, good eye. Okay, so let's turn on our networking so that we can SCP our app over. He still does say no encoder here. And we can see at exactly what line, so line 81. So it is, in fact, this get encoder call that is failing. So that's good. Now, the question is why? So we should look at what this call is doing. This is like libdrm, this basically wrapper for ioctls to our kernel device, where ioctls are kind of like out-of-band I/O control functions, handled by drm ioctls. So if we look for like when we register our driver, we say like, hey, our driver has these like file operations you can do on him, and they are handled by like the DRM subsystem, DRM octal. Cool. Cool, cool, cool. So in here, we can look for get encoder here. And this function is what we expect to be called. Now, we could be wrong about that, but that is what I expect. So why would this be failing? We don't know yet, because we're the how do I say this? The call to the libdrm wrapper does not keep these errors. He just returns null. But I wonder if we can get them out of error now. Like when I call ioctal, erno is set to indicate the error, right? So we could just try to print the value of erno at this point, and that will give us a clue. That will give us a clue. So let's try to do that, because I'm pretty sure nobody else does any sys calls in between here. So if we just do like erno, can I get that value somehow? Like zig erno. I guess it's like stood c erno. What does this do? Looks like we can just call this function to get a pointer to a C int. And then there's also this constant here. Yeah, it looks like we just call erno. Looks like. Maybe. We will see. Erno is a number, which is got by dereferencing the pointer that comes back from here, I assume. And for good measure, we'll just double check that it's clear beforehand. Just for good measure. Yeah. So here we foolishly cannot log the erno here because we say or else return here. So instead we should do this. Then we should see what we want to see. He does say erno 2, so the value of erno has changed, which is a good sign for us. Writing your own GPU driver because the Nuvu driver's always been dog shit, question mark? No. The goal here is to understand the Linux graphics stack. And so we are trying to basically write our own GPU driver for our own fake GPU just to understand what's going on under the hood. Just to understand. Okay, so we know that he's returning error 2, which is not really that helpful, because that's not a word for me. But we can just go to wherever the fuck we were here, and we can jump to here and try to figure out where 2 is. 2 is enoint. So this seems likely to me that the DRM subsystem is trying to look for the encoder ID that we asked for, and he can't find it. So it'd be interesting maybe to set a breakpoint here and see if that tells us anything interesting. So I guess we need yet another window. Yet another window, and we're going to change our run script to stop itself and wait for GDB. So what happens here is like QEMU, the virtual machine, has like a GDB server built in, which allows us to do some pretty fun stuff. It's like he kind of knows that he's loaded the Linux binary at like a certain memory location, and he knows like what instruction is being executed right now and the memory of the entire child virtual machine, so you can do everything that GDB needs to do. So it's kind of cool. So let's set a breakpoint here at this line. I guess we could also set a breakpoint kind of here at the top of the function, or at DRM mode get encoder. And we can kind of see how this works. Now, I don't really know if our GDB breakpoints are going to work, setting them off rip like this. We might want to kind of delay the setting of them, but we'll kind of see, because we kind of changed the way that things are laid out, where we have like loadable kernel modules and stuff like this, but it looks like he's happy. It looks like he's happy. But we do not see our breakpoint get hit, which is a little concerning. A little concerning. So can we like breakpoint here? He says he's happy to set one there, but if we run our test app, oh, there we go. There we go. We are chilling. So we expect Oh, we thought we were going to see here, but it looks like we did not, right? So if we run this again and we hit next, we print encoder here. No simple encoder. Okay, that's confusing. We went from 345 to 317 in the same file. No. What the fuck is going on here? Hold on. Run the app. Step. Oh, I see. This DRM encoder find must be like an alias to some other function. Can we finish here? Value returned is 0. Sounds like... Why is like the stepping so fucking broken? Maybe because of optimizations. Can I break on this line specifically? I guess not. Can we just like step into this, finish? So we did return null pointer. So we can probably, it does seem like this is probably the problem. And can we like look at what we expect to happen here? So we have an object IDR, main KMS tracking ID, from our mode config. So we set up a mode config somewhere. I remember doing that. Sphero derv. I wonder if it makes sense for us to try to like look at that stuff. So I guess in our mode config, we don't really set up anything encoder specific here. But we do call encoder attach here to the connector. And we did see the encoder in our mode somewhere. So I'm curious about, I guess, what objects we have in this area that are encoders. That's something that we want to look at, right? So he's calling object find, and he's just trying to loop through somewhere all objects and looking for types of object encoder. So like, where is this used? Surely somebody must add objects with these things too, right? In DRM encoder init, we do in fact do that, right? So this is called by our driver somewhere, I believe. Let's just kind of take a little backtrace look skis. Not here. Not here. I thought we called, oh, maybe DRM encoder init. Oh, this is a recursive callback. He's confused. Here we go. DRM simple encoder init. We do call this, right? Because we go from here, Sphero probe, into simple encoder init, right? Which should make it all the way down into this system. So I guess the question is, why is it wrong then? Right? I guess theoretically, maybe our encoder at this point doesn't have his ID set. That's a possibility. Well, I need to write C on a Linux machine. I'm currently on Mac and using NVIM and when I go to def for a lib, the dogs are horrible. Oh, like, you're like, wow, the Linux kernel has documentation, that's cool. I guess it is kind of cool. I've never really thought about it. This maybe also is a problem. I think we saw earlier in happy hour that there is a big warning here that says that our encoder has an incorrect possible CRTCs. So maybe if we correct this, then the encoder will be happy. There's a very real possibility there. But maybe not. Maybe not. So how do we want to do this? First of all, what is that line at 319 in where were we? DRM encoder.h. Yeah, okay, so we were here. And so this DRM encoder find definitely returned null, and that's definitely why we have found the right failure location. Yeah, because it seems like we've added one. So it's possible How does he do this? He has an ID associated with him already. The encoder ID, I guess. Yeah, yeah. So the thing that when we came in here asking for ID 0, we try to find this thing with this ID. Okay, come all the way in here. Boom, boom, boom. So here we pull this thing out of this radix tree, whatever this like IDR thing is. And I guess we want to know which one of these things are failing. I expect that this ID 0 is incorrect. That's kind of my expectation here, but I'm not really sure. It'd be maybe interesting to breakpoint on this stuff and single step in here and see what happens. Kind of interested in that. I guess we need to reconnect our GDB. So we give him a second root. And then I think we forgot to set the breakpoint here. So I want a breakpoint right fucking here. Oops, continue. And I guess we want to wait till we hit our other breakpoint, which I guess is not being set here. Okay, so enable to continue. And can we, what were we trying to discover about this? I expected that this is, the type is wrong here. Okay, so what is the value of this? PX type. EO, 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 EO. So this is an encoder. Okay. So we have, this actually does match the type that we expect, which is a little surprising, right? So here we say if object type and type is not equal to this, and type is not equal to type, we return null. But type should be equal to type. What is like our, oh, type is what we asked for. We want what the object type is. Oh, obj is null. Obj is null here. So ID 0 must be fucking bogus. Which would make sense. So the question is, why? It's whoever sets the connector's encoder ID, right? Like we are getting this encoder ID through the connector interface. So whoever sets that must not have set him. Right? I kind of expected like this attach encoder thing. Oh, okay. So before they used to do this direct assignment, the connection is a logical one and the responsibility of the core. So drivers are not expected to not mess with this. Note that the error returned here should be good enough. Right, so they say here are possible encoders, which means here that someone must set this at some point. Right, presumably this is done on registration here. Presumably. And presumably this is not working correctly. That's just kind of like hand wavy what I'm expecting here. And it could be that it's because the CRTC stuff isn't hooked up. That's very possible. Very, very possible. So can we look at that like warning log here that says, hey, you fucking need a CRTC. Bogus possible CRTCs. Let me look for that. Bogus possible what was it? Bogus possible _CRTCs here. So he doesn't really return anything here. He just kind of logs it. So there's actually nothing really to worry about there, I don't think. Okay. And where does this come from? From validate on register. So like right off rip, basically. Right off rip. So I'm really more interested in who sets like our connectors encoder ID. Well, I guess who sets encoder ID when we call DRM ioctl, in here we call get connector, and this is where we're tying this shit back, right? And one of his outputs is an encoder ID. So where does this come from? Aha, 0 is invalid. Aha, aha, aha. So this is failing. Getting encoder for connector. He goes, hey, we don't have one. So we set this to 0. And then we're trying to fetch from 0 and then falling the fuck over. That makes a lot of sense. Okay. So then, how the fuck does this get fixed? That is the question. That is a question. So, atomic helpers set this like best encoder. Set best encoder. Okay, this looks promising. So update connector routing on atomic helper check mode set. So we do have atomic enabled, which makes me think that we are probably going to be calling this somehow. I guess the vert IO GPU set this and we didn't. So we actually might not go down this path. Which is kind of interesting to some extent. So here they call atomic check. Was that where this came from? Helper check, update connector routing. Yeah. So we, I guess, are not in that path, but maybe we're supposed to be. Do we have connector state? I don't really know what this means. DRM connector state. This is protected by this. I mean, it could be. It could be. We should probably breakpoint on get connector and try to inspect which path is taken there. So maybe we do just like breakpoint here. Maybe. All right. GB-X. Okay. And let's see what happens. Okay. So we do in fact have connector state. And best encoder is null. Right. So it seems like the expectation here is that because we have said that our driver supports like atomic access, which I don't really know what it means, but we're just kind of copying it. We're following someone else. This is expected to be set and it's not. So I bet that we basically need to follow what vert GPU display is doing here and use these atomic options to propagate onto like the generic DRM subsystem. So can we see like atomic check? This is the only hook to validate a mode set update. This function must reject any mode set and state changes which hardware driver does not support. This includes, but is of course not limited to blah, blah, blah. So it sounds like maybe, oh, and then the atomic commit, is that where this stuff actually happens? Yes, 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 yes. So I think that when they talk about like atomic commit and atomic set, my gut kind of says we're on this path of like, you set all of these things that you want, but they happen in one shot. Bump, 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 one moment, he vomits on his sweater, something like that. Anyway, it doesn't fucking matter. Yeah, so I think this basically says like we preset all this stuff and then we actually have to do it. And we probably are presetting some stuff and not doing it. That would be my guess. So let's see what happens if we apply these functions to our driver. So it's these. Boom. Let's see what happens. So I just go make. And we quit here, and we run here, and then we GDB X here, and we hit continue, and then we go over here, and we wait for the thing to boot all the way, which takes a few seconds. And then we run root and test app, and here, he's still null. He's still null, which isn't great. It was not great. So it'd be nice to kind of breakpoint in here, maybe, just to see if that happens. So we saw somewhere like best encoder got set somewhere, right? Where did we see that? Is it in our history somewhere? Atomic helper. I think it was like here. Yeah, so set best encoder. We saw come from update encoder, blah, 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 atomic helper check. Which came from here. So I think we want to breakpoint both on like the actual assignment here. As well as up the call stack on like our entry point here. So we just want to see like, are we really going into this path, right? So this is the thing that we assigned just now to our thing. And like, let's see if this is called. And then let's also see if we make it all the way down. And if not, then we can kind of like bisect between those two things. I think that makes sense. Bump, 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 bump. All right. So this seems like it's kind of doing what I would expect. We are getting into this thing from someone calling our config funcs atomic checks. That's good. Now, if I continue here, we do not see that he set best encoder. So somewhere between here, someone's rejecting this essentially. And I guess the question is like, where? So this is supposed to go into helper atomic check mode set. So that's like literally like the first line. Then he gets in this function helper check mode set, and he's supposed to get into update connector routing, right? Here. So what is going on here? It'd be interesting to see if we hit this. So we add this to our list of breakpoints, I guess. And is there like a rejection case here that we need to look at? So we might return early if there's like conflicting encoders. So we might want to just breakpoint kind of like at the top of this function as well. Break at the top of this. Check if we go into update connector routing, and then in update connector routing, we were looking for somebody who calls like set best encoder here, right? Here, here, here. So maybe we'll just kind of step through update connector routing if we get there. If we get there. All right. So here we're at line 631, which is the first line here. And I guess we're just going to step through this and see what happens. So is this where we expected? Where are we expecting to see us get into this set best connector thing? Encoder, sorry. Update connector routing. Is that where we're at right now? Oh, no, we're not. Can we just continue then? We were actually in check mode set. So we actually never got to update connector routing, actually. Right. This is where we were. We were kind of wanting to walk through this. So what happens here? We're for each old new connector in state. I guess we just kind of breakpoint like here and see what happens. Fuck all the other breakpoints. There's too many. Too many. And I don't know where they all are. So we're going to start over. All right. So we do not have a ret here, so we do get into this for each old new thing. And if we jump through this, he goes straight to 1106. In a different file, hello? Durham Atomic H, 1106. Durham Atomic CRTC needs mode set. Oh, so we're down here. So it's almost like whatever this loop is doing, we like didn't go into it. And he just immediately skipped down here. It's kind of like what it looks like happened. Yeah, and we can see that here. He goes from 685 to 731, like, immediately. So this loop has nothing in it, okay? Okay. So what is this loop supposed to do? Iterate over all connectors in an atomic update. Connector, so old is the cursor for the old state. Okay, new is for the new state. Okay. And I is an iteration cursor. Okay. Sure. So this just goes. How does he know like the length here? What's the stop condition here? For each if condition. Jesus, dude. I don't know what I'm looking at. This is a condition that goes in an if. So he says this and this, comma. Oh, I see. So this is always true, the second half, but is like the iteration state trekking. And then this is the actual check. I think this is running for the vert IO drivers, not yours. I don't think so. I don't think so. But we can take a peek. Oh. I guess we could be in this breakpoint. Yeah, you're right. It does kind of look like that. I kind of assumed. I made an ass of me and me. Good point. That's even more confusing. Because our thing should run at some point. Okay, that's a really good point. Good eye. Can we just disable theirs temporarily? That way we kind of only have our one thing to worry about. Yeah, I guess we just don't even get to this path at all. That is a good eye. Thank you, thank you, thank you. So what the fuck is going on there? Let's make sure that if we try like looking at like anything else, like let's just put a breakpoint here, that like we see anything happening, just to make sure that it like works correctly. Good eye, good eye. Yeah, so this does happen, and then we just never get into that stuff. Okay, so that's a good clue, actually. We were kind of looking at the wrong spot. So thank you for that. But we should get into like this config validate, right? Where did we think that the backtrace for this thing was? We were looking at best connector. So I think that part of the test was valid where we checked the connector hookups because that was when we were running test app on our device. So we're looking for like best encoder equals, right? That's what we're looking for. In here. This is where we're looking. So we wanted to see, is this getting called at all? It should be, but maybe not. Is this getting called? The check function that we hooked up, where we think that this is like a possibility of something that could happen. So here we get into register, and they never call atomic check. Okay, okay. So why the fuck not? Why the fuck not? Because this is where we expect this to happen. So where does this atomic check come from? Here. Atomic check only. Which comes from like commit or non-blocking commit or atomic non-blocking commit. Interesting. I almost want to go back and look at the backtrace for the case where we hit this breakpoint in the virt IO GPU driver. Right, so we were in virt IO GPU probe, DRM client register. Do we call that? Is there not some atomic flag you set? We do set that though, as far as I understand. DRM client register in virt IO GPU probe. So virt IO GPU derv 106. That's what we're looking for. They call okay. Set up fpdev emulation for gem shmem helpers. So this is where they are actually getting. This is where they're actually getting the best encoder hooked up, as far as I can tell. So I wonder how I'm supposed to know we have to call this. DRM client init. So initialize the DRM client. Use register to complete the process, right? Okay, so these are all related to the frame buffer helper though, right? So here they initialize this client as like a frame buffer client of the DRM subsystem. Interesting. I would have thought that this doesn't need to get done. Interesting. Okay. Yeah, it feels like everything should have got hooked up in here, but I guess that's not the case. unless like maybe our stuff gets called when we run our test app. Like it could be that like this is only necessary. Like this just happens to be where it's called in their case, but it doesn't have to be called there. Right? Like if we call okay, so let's set a breakpoint. Make sure we have a breakpoint set. In atomic helper check. So we have one set there. So if I run test app, oh, he's running on the wrong card now because we removed one. Hold on. We do need UDHC. We need like a network address. I think it's like this. And then we want to set this back to card 0 because we only have one card. So here we're still not hitting that at all. We're not hitting that at all, which is kind of confusing. I would think that like there's some sort of I would have thought that the the workflow that we have would trigger that case, because surely not everybody calls this fbdev shmem setup. This doesn't even have to happen. I thought this is for like emulation of fbdev, which is like a feature you can totally disable. Like that's a thing that the kernel doesn't even have to support. I saw in the kernel configs. Yeah. Not this. So what does this even do? Initialize a DRM client. Okay. Okay. I don't really understand here. So maybe you need a client in it to exist. DRM client open. Clients running in the kernel, like fbdev and bootsplash. But like, yeah, why do I need one of those? I wonder if this is how like mode setting gets set at all. Maybe we have like in our test application, we are assuming that somebody has set up the like current mode. And if we don't set up this like frame buffer client, we're kind of like in an uninitialized state. That's kind of my guess. So if we look at like Sphero derv C, and we go back to this like atomic check, who calls this? DRM atomic check only. So like mode set commit atomic, mode set check, mode set commit locked. Like how do I like when I'm looking at modes, we like sometimes set a particular mode, right? That's like a thing that we can do. And surely in there, because somewhere in our test application, we're calling like, what is the preferred mode? That's like a thing that we ask for. Get preferred mode. Here, so we look at connector modes and we look for the DRM type preferred. Okay, but there's also, let's look at the, like way back, we had like this example of DRM Linux kernel embedded something or other. Like there was this guy who wrote a blog post on how to output to the DRM buffer directly. It'll be in our notes. So it would have been in like this notes here. What did he do? Because surely, I just do not believe that this is the only way to hit this path, and so I really want to understand it a little better. Dun, 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 dun. So how did he pick the mode? Get the resources. He looks for the current connector, adds a frame buffer. Wait, where's his like GitHub? Where's his GitHub? Here we go. Mode. Get encoder. Get resources. So he calls get resources. He looks over the connectors. He gets the current connector. I remember seeing something about being able to like set the mode, which somebody has to do, right? Like somebody has to set like what resolution do I want to be? I'm pretty sure somebody has to set that. But I don't really see it anywhere, which is kind of interesting. Kind of interesting. I would have expected one of these many ioctals to be that. KMS DRM set resolution. This isn't really what I'm looking for. Maybe the idiot can help us. Is there a libdrm call to change the KMS mode? Question mark. Set CRTC. Ah. Is that when like resolution is applied? Yeah, he applies the mode here. Okay. Okay. So in that case, we could maybe look at like if no encoder is hooked up, but it is a possible encoder, maybe that's enough. So right now we're trying to be like, which encoder is used for my connector? And then trying to work backwards from there. But we do have possible encoders. So I'm curious to see if that works. So instead of calling connector encoder ID, which is 0, which is not set, we could look at encoders here. I'd be curious to look at encoders 0 and see what that does. Okay, so that actually correctly finds an encoder. So we could maybe say, hey, if there is an encoder already set up, fucking great. Otherwise, just pick one. That feels reasonable to me because like it's kind of saying, according to ChatGPT, which fucking idiot. When we call this call, an encoder might be kind of like set up for us automatically. Connectors, mode, and CRTC. Yeah, so I guess it's kind of saying like the CRTC will figure out which encoder it needs to use to get to that connector. Right? Like maybe you have 3 VGA ports and you have 3 VGA encoders. And they can kind of like be mismatched in whatever way they want. Okay. Okay. Sure. Let's kind of go down this route for now, and then we'll come back and we'll see if it makes sense. So we'll say encoder ID is equal to this. If it's 0, then we return connector encoder 0. But fix me check if num encoders is greater than 0. So I guess this. else if connector encoders. I guess we want if connector encoder ID is not equal to 0, we pick that one. Else if count encoders is greater than 0, we can return that. Else return error no usable encoder. Then here we can use encoder ID. Okay. Okay, we got past this part, which is good. Now we're back onto get CRTC. So all of this was why can't we find an encoder? I'm not like really 100% sure that this is the right fix, but it feels kind of reasonable to me. So like, fuck it, we run with it, right? Fuck it. So this is actually CRTC. CRTC time. So back to the little diagram, wherever the fuck that is, here. We now have this, we have this, we have this, we have this. We need these two things. So we work our way back. We get the CRTCs associated with this thing, which we set in our driver. Here, theoretically. Right, we say, hey, which CRTCs could we connect to? And right now we have 0, because we have no CRTCs. But we have to make one. So, what do they do in here? They set index here. And here they create a CRTC like this. They say, hey, I want a CRTC baby, and then they have helper functions for that CRTC, which look like they do real work. They look like they do real work in some way. It looks like they kind of send off to the GPU that like, hey, we're not being used right now, which is fine. Which is fine. I guess for now, we kind of just try to do as little as possible. Right? So I think that we do in fact want to call init with planes almost certainly. Let's see. Initialize a new CRTC object with specified primary and cursor planes. Okay. Where the cursor plane I think is like literally to show the mouse on top of stuff. So he passes in 2 planes. Do I guess, do I need a cursor plane? I don't really want a cursor plane. That sounds fucking stupid. I don't want like a custom hardware tracking of the cursor. That seems stupid. I can just do that myself. But it does seem like that's kind of expected. I was also reading in this like a trip through the graphics pipeline that someone sent the other day. They were kind of talking about like somewhere in here they were talking about like hardware specific cursor handling, which is very funny. So it's like a thing that is like normal, I guess. But I guess we will call this for now, and then we'll figure it out later. We will come back for if we really, really need a cursor plane. Which means that we have to make planes. Right, so here they have created a plane with universal plane alloc. Okay. So here they're saying, hey, we're allowed to be ARGB 8888, essentially. I don't know what the difference between ARGB and XRGB is. I think X means no alpha, I guess, would be my guess. Would be my guess. Hardware cursors are goated. I mean, maybe you know that. I don't know that. That seems crazy to me. It seems like if you need hardware cursor, why don't you need hardware like Windows, you know? They're like the same shit. Like you should be able to like kind of have a buffer that you want to update a certain, like you should be able to like update a small amount of the screen kind of anywhere with any reason, I would think, but maybe not, I guess. So they call this universal plane alloc, and then add with functions, where functions are hello? Oh, here. Okay, so they have like helper functions that are different for cursor and primary plane. Gotta get that low latency on the cursor for good feels. I guess maybe. Aren't hardware windows the thing? I didn't think so, but maybe. I assumed not. I mean, I don't see any reference to them here, but maybe we'll get farther down the stack and we'll find them. Okay, if we are the primary plane, they enable damage tracking. So this is kind of more what I was thinking about, right? Where your frame buffer says like, hey, there are parts of this thing that have been updated, and I would like to update those parts now. And I guess they just. So what does this do? It's a hint to the kernel that could be useful to optimize internally. User space can ignore dynamic clips property. Sure. I don't want to read this. I guess we should though. Drivers that are interested in damage interface for a plane should enable damage clips property. Sure. There are frame damage and buffer damage. Type of damage handling inputted depends on a driver's upload target. Drivers implementing per plane or per CRTC upload targets need to handle frame damage, while drivers implementing a per buffer upload target need to handle buffer damage. Sure. Okay, I think I get it. So it seems like we probably want to allocate 2 planes. What does their like cursor plane update thing look like? What if we just don't update the cursor plane? I think that'll be fine for our like user space usage for now. I do not think that we are using the cursor plane in our little sample application. So, okay, I guess we need some plane helper functions. Seems like we're gonna need. We're gonna make like static and like make CRTC or something. I don't know. Sphero make CRTC. You put windows on overlay planes? I guess that makes sense. And we are going to have to do something like take these helper functions. And where does this get used? Here. So it's like we make a plane, right? And we use our Sphero GPU primary helper funcs. I guess we should I guess maybe we do like cursor helper funcs. Just kind of nulls this shit out. He just doesn't do anything for atomic update. We check this stuff. And I guess we should enable damage. I guess. Seems reasonable. So that's like him making a plane. And once he makes a plane, he makes one for the cursor and one for one for cursor, one for primary. So we're just gonna say like primary plane is this. Then we'll just do this again, but for the cursor plane. Okay, I don't really know. And then we're gonna init this thing with planes. And then our encoder will have a possible CRTCs of 1. I believe is how this is gonna work. Okay, so now we just have to figure out what the fuck this stuff does. So they returned a DRM plane out of that thing probably, right? Plane is a DRM plane. So here, if we have a primary plane issue, we ditch that shit. So pointer error this thing. Then we have to do the same thing here. I guess we want to do like cursor plane here. What's he mad about here? Does this stuff have to get wrapped because pointer error is like kind of some sort of fucked up shit? Or is it error pointer? No, pointer error should work. I don't know why he's mad, but we'll kind of just keep plowing. Is that spooky Halloween hoodie? Yeah, it's spooky month, so I'm allowed to wear this one again. Index here, we're gonna have to figure out eventually, but whatever. Primary plane instead of plane. Oh, that's true. That is true. I wonder why my syntax highlighting is all fucked up though. Oh, because I didn't copy this whole thing here. I fucked up this. I see. This goes here. Nice. There we go. Much better. So I guess we want to do our typical like something like this. And then here we're gonna have to have like a label for like error. And in this like error section, we're going to free the primary plane. So can we do like I don't really know how can you like if this DRMM stuff fails, can you like free it anyways? DRMM free. Like, is that a thing? It's fucking not helpful. So like add alloc dr and then add dr. Del dr seems like what I want. DRMM k free probably is what I actually want here. Depending on if that's like the alloc free function that they use for their thing. So the DRMM stuff is like when it attaches itself to the dev handle as like a list of objects that have to be freed. And so I'm trying to figure out like if I don't want it to stay attached anymore, then like what's like is that a problem? Right, so somewhere he's going to call this. And he should have some sort of like delete function associated with him. I think that's how this works. However, I don't really see that here. I thought that's how this works. Otherwise, like, how does it get freed? Like, it's gotta be in here. Oh, here, I see. List add dev managed resources. Okay, but like, how do they tell him how to delete it? Am I stupid? Ah. Aha, ha, ha. So its release is null? What the fuck? Final DRM dev put. Memory can also be freed before the final DRM put by calling DRMFK free. I guess we'll just do that because I'm not going to find it in the code right now. So we'll just have DRMMK free for primary plane. Sounds like that's what we're supposed to do. So here, I guess we'll kind of do this down here. Boom, boom. And then we'll say RC equals this and go to error. Great. Now, on the future, guys, if any of these things fail, we're going to have like an error cursor plane, right? Who's going to look very similar. Which means it's going to be like error. I guess this should be called error cursor plane, and this should be called error, kind of just generally. Right, so then we can say go to error cursor plane. Wow, look at us go. This encode is weird. Okay, so we need to add helpers to our primary plane with our... something about this doesn't feel right. Where do we copy this from? It's called DRM helper plane add. Ah, I see. So yeah, they do this for each of them. So this is primary plane and our funcs. What is funcs here? Helper funcs. DRM plane helper funcs. Yeah. So why do we have to use that twice? Why do we have to use that twice? Am I stupid? Oh, these are two different things. These are our plain funcs. My bad, my bad, my bad, my bad. There are plain funcs and there are plain helper funcs. Oops. So both planes use the same set of Sphero GPU plain funcs, but then we use Sphero GPU primary helper funcs here and cursor helper funcs here. Okay. All right. Then we enable FB damage on the primary plane, which I guess can go up here. And then we initialize our CRTC with these planes, I guess. And certainly, can this fail? We don't know yet. We don't know yet. Okay, let's try to implement some of these. Here, we'll do this for now. And then we'll try to just kind of fix compile errors. So primary plane, we're just kind of fixing everything to index 1. We need our DRM device. Okay, so that's going to kind of go here. Formats and end formats. It looks like we have to say which formats we support somewhere. So we do like vert IO GPU or display. Here, formats, end formats. So these are set kind of as like static constants. Okay. We are going to just force XRGB here. And we'll say, fix me, cursor might want ARGB. Or else no alpha. But fuck it, I don't care right now. So here we'll say Sphero GPU formats here. We have 1. And what was type here? DRM enum, DRM plain type. Ah, okay. So it's DRM plain cursor, plain type cursor. DRM plain type primary, and this is cursor. Okay. All right. This needs to say cursor plane or here. And then we're back down here. So this is DRM dev here. We need a CRTC to initialize. So maybe we also take the Sphero dev here. Like this. And that way we can say priv CRTC, which means that we need to store a CRTC somewhere. So we'll kind of do it like this. Then we take in our primary plane and cursor plane, as well as our CRTC funcs. Okay. Okay, and then we need to implement this thing. Both of these. So we'll copy paste these as well temporarily, and then we'll figure it out from there. Okay, so CRTCs, we have CRTC funcs and CRTC helper funcs. Spheroderv here. So vert io sphero. These are all just DRM pass-throughs. So I think we don't have to worry about that one. And what about their helper funcs? These are actual implementations from them, which is a little scary. So for us, instead of implementing them, we will just not implement them. Wow. Okay. Okay, because we're just trying to follow the errors to get something sane. So he says we don't have a CRTC thing here. I thought we called it, we called it DRM CRTC, so we'll name it correctly here. And it looks like this label is unused. So I guess that kind of indicates that this stuff cannot fail, except it can't. This can definitely fail, right? So this returns 0 success, error, code, failure. So here we say RC equals this. If RC is not equal to 0, we go to error. Oops. It's here. Boom. And then this can't fail, right? Void. Void. Yeah, okay. He doesn't like that DRMMK free is not in here, so we will just kind of add the appropriate include. Too few arguments to function call, so he wants the DRM device as well. Okay. Cool. I think we're pretty chilling. So I guess we should call this function. So we take our private data and our DRM dev like this. And I guess we're probably chilling. Super chilling. We're gonna say note assumed index 1. And maybe in here we're gonna say like const idx mask is an int is equal to 1 shift left by 1 or something. Assumed index 0, sorry. Yeah. Because this takes in the possible CRTCs. So maybe we do like a static const sphero possible CRTCs. Like this. Just to make it clear. That way we can say like assumed single possible CRTC at index 0. And then later, if we ever want to change this, it will be obvious that it's wrong. Because we can just look for references. All right. Make? How fucked is this? It builds. Does it run? I guess we probably don't need GDB quite at this exact second. So I will turn that shit off. And we'll see how fucked we get. No CRTC. No CRTC. confusing. If we look at DRM, our resources, we do in fact have a connector now, which is a big win for us. That's so big. But we might kind of have the same problem where the encoder like might not be linked to the CRTC yet, the way we expect if we had called frame buffer initialization in the kernel driver. It's kind of the assumption that I have right now. So I bet we can probably check here, and we can probably see that encoder CRTC ID is 0. Encoder CRTC ID. Oh, we don't even have to do this. We fucking print log the encoder already, so we can just look at it. So CRTC ID 0, but he has possible CRTC IDs 1. So I guess what we do is for now we'll say, have you figured out why the smiley face is not smiling anymore? I have not looked. That was confusing to me. And we will come back to it probably. Maybe. I don't know. Because yeah, he should have worked. He was working like literally, I tested it literally like right before stream started. Like in the break time, I checked it and it was working fine. And then as soon as I started stream, it didn't work anymore. So I don't really know what caused that. But you know, we live, we learn. I figured we'll kind of like naturally get there. When we try to actually use the thing in our version. I figure we will have to tackle it there. Okay, so we have its CRTC ID here. If it's not 0, we use the encoder CRTC ID. Otherwise, we look at encoder possible CRTCs. If this has bit 0 set, wait. Are they one index then? Hold on. They start at 0 and work their way up. So possible CRTCs gets 1 shifted left by index, i.e. so the first CRTC should have index 0. In which case, if we have index 0, why is it a problem? Because we're trying to use 0. We could look at the ioctl. I'm kind of assuming that it was the same problem with the connector, but now I don't really believe that. So if we call get encoder, he calls get CRTC. So his output here has CRTC ID here. What is this? What is this comment? CRTC ID is the ID of CRTC. Yeah, of course. How does this make it in? Okay, this has like the same thing though, where they set 0, which means that index 0 can't happen. It just feels like it shouldn't. So I wonder if there's like a +1 that happens somewhere here. Yeah, something about this feels wrong. So when we call get connector or get CRTC, get CRTC, his input is this. Which literally just does all the stuff we were looking at before. Where they like look for an object that matches that ID of that type. Okay. Can we look at maybe the output of DRM or like resources? Can we look at the CRTCs there? I'm just curious now. Maybe the IDs are not what I expect them to be. Maybe it's like the first CRTC which has an ID of something else. You know what I mean? Like it could be that you have like possible CRTCs is like 0B1101, which means that he can be like the first, third, or fourth CRTC. And then you have to actually extract their IDs by looking at the resources. Right? So I want to look at resources CRTC 0. I just want to see what this is. So CD, oopsies. I guess usually I'm doing this in this window. We don't have our thing open, I guess. I guess we do need to run the virtual machine if we want to run the virtual machine. That's a classic. All right, udhcpc IENP0s3, nice, and then here we should be able to run our little build and test, and we see CRTC 40. That makes sense. So we're gonna say here in our kind of workaround, our CRTC ID is going to be, if it's not 0, we use that one. Otherwise, we check that he's using the first index, and then we look at resources CRTCs 0. Otherwise, return unusable CRTC, and we use CRTC ID here. He doesn't like this, is not equals to 0. Okay, there we go. So that got us a CRTC. And now we move forward and we try to map the memory that we allocated way back somewhere else to try to write into it. And I believe that's an easy fix. So I think that we are at 012740, and let's say map frame buffer memory. This should be pretty straightforward. So we saw a couple days ago that invert IO GPU, how did they do this? Somewhere they said that they initialized these like file operations here, down here. And they just define their file operations by doing define gem fops, which is this generic thing, and they have mmap derm gem map, right? So there's just like generic driver subsystem mmap stuff. We were like, I don't know if we're going to use gem. At that point, we weren't really sure what was going on. We now know that we are using gem. So I think that we just bypass this, right? So I think that we just kind of replace our fops with this. Right, so our version, we basically copy pasted everything except for the mmap piece. So I think that if we do this, it should be fine. And that might be all that's required to do mapping. Because our memory buffer is already kind of backed by shared memory, so there's like, it should just work. It should just work. We're making a lot of assumptions along the way, by the way, because fuck it. So let's see if we get farther this time. Okay, so here we now null point our dereference at commit, which is very likely we render our smiley face, we call this, and we just segfault because we didn't actually implement whatever has to get implemented here. That would be my guess. So here I'm going to say print std debug print hi mom, I'm about to. Oh, okay. We can do a little double entendre here. If I say I'm about to KMS, we can say that we're kernel mode setting here. But also, there's a second meaning to that that kind of fits nicely with this call to die. Perfect, perfect. Okay, let's restart our virtual machine. And let's look at root and let's udhcpc. I guess to satisfy Twitch, we can say in VM, because that's, you know, it's like when you say allegedly. Now they can't ban me. Yeah, so he's like, "Hi mom, I went to KMS," and then here he dies. So I think we're chilling. I think that this was expected to me. So I think what we can do is we can try to look at like where this line is. Which we can pretty reliably assume is going to be calling some function that we didn't set up. So we can be like, yo. Let's say, can I look at like line? Oops. This info line, I think it's commit helper planes 2803. So wait, what? Sorry, it was DRM atomic helper 2803. Yeah. Yep. So he's calling. Oh no, wait. Oh yeah, so funcs is not defined here. Funcs equals plain helper private, which gets assigned here, which we do call actually. And he is guarding some of these. What line did it say? It's like, well, on 2803. Oopsies. Oh, yeah. So he's calling atomic update here, probably, which we haven't set. Unguarded. It's probably just a little bit off. Right? Because here we had atomic update just commented out, right? So probably we call this, we set this up. I mean, we can check this, right? We can set a breakpoint, like, literally right here. And we can confirm. It's best to be sure. I always harp on you guys saying we should find the reason why stuff happens. And I think just skimming over that would be doing a disservice. We do need to turn on GDB, huh? We do need to turn on GDB. And then here we run GDB-X. Okay, continue. We go here. We wait a second. We run root test app. Okay, and then we look at pfuncs. He sure is about to call atomic update right here. Yep. All right. So let's do this. And then I guess we will kind of have to figure out what this has to do at some point. But what if we just didn't find out, what it has to do? And we just kind of pretend that we've implemented it. And then figure it out later. Let's just kind of like, follow the errors. Yellow. So I guess, what do I want to do here? I probably want to run without GDB again. Run. And I presume we'll just see another crash. We do see another crash at commit planes here. So this is probably a very similar problem. So we can do like the same thing. We say info line at this address, which is at 2803 in atomic helper. Right. So we actually could have looked a little bit and seen an immediate, oh, there's going to be atomic enable here as well. Like literally in like the same 2 lines. But how come we don't have that commented out anywhere? Oh, because that is guarded. Wait, that was a guarded call. Yeah. So they only call this if it exists. So why are we still crashing in this area then? I'm a little confused. I would have expected that to fix it. I did build, right? Did I save? I saved, yeah. I built. I guess we turned GDB back on. I guess. Because I don't get it. I guess. How's it going? Not too bad. How are you? Root test app. Okay. So p-funcs. Oh, he's still not set. Why not? What file is this? It's a DRM atomic helper. So funcs. Okay, so where funcs gets set by plain helper private. Okay, so this looks like it has stuff in it. Okay, so this has definitely got some stuff, but it's all zeroed out. Did I only fix this for one of the planes? We had cursor helper and primary helper. Yeah, so here we had to do the same thing. And we'll call this, I guess we'll call this plane update. They had different implementations in our invert IO GPU for primary and cursor planes, but we don't want to deal with that shit right now. So we'll just kind of give them both null. There we go. That makes more sense. That makes more sense. All right, let's see if everybody's happy. Let's see if everybody's happy. Okay. So p-funcs. Yep, atomic update is so chilling there. And now what's happening? It looks like he... Oh, does he just end? Oh, right, because we sleep for 5 seconds after we do this. So from the perspective of the app, it's working. Now, nothing is happening, but I think that means that we should be able to look at the memory at this point and try to copy to the host so that we can write it out to an image. I think that's the thing we should be able to do. So I'd like to somewhere we did we didn't really write down where we were here. It was sometime before now, I guess. This was like finish CRTC. Fix CRTC crashes. And yeah, let's see if we can like inspect the host memory in there somehow. That'd be cool. So my gut says that since the only thing that we have done here, in terms of like talking to, like the only function that we have here is plain update, right? So like this must be where we're supposed to trigger on our GPU to do something. Now, probably these things we could also do stuff, but say we don't actually have any like this. To me, this looks like prepare and clean up FB would be like managing hardware resources. So like telling the other side, like, hey, could you take this buffer and like use it for frame buffer? And you're like buffer ID 0, and here you go. Now, we could choose to not do that if we want. We instead could we get to choose what interface is, and right now I'm kind of thinking that the interface should be like write to PCI register with location plus size of buffer. Then when we write that, like the GPU just does its thing. Now we're gonna have all sorts of problems there with like resource resource locking, right? So like if we try to write something, then the GPU is like, okay, I will use that now, and he like just starts trying to read that memory. If we overwrite that memory as he's writing, we might run into problems. But we don't really care about that right now. We don't care about that right now. So we'll just say that our GPU just will like, you just have to like guess how long a write takes. So from a user perspective, or we just like don't support tear-free rendering, in which case it's fine, right? Here we just kind of say like, look, bro, like sleep 400 milliseconds or something, just like to be safe after this. But we don't even render multiple frames right now, so we can just tackle that problem later. Later the answer will be that we like create like a queue of like commands, and one of those things is going to be like, here's a frame buffer, and like draw it, please, right? And then later we'll have like a queue of responses, and he'll be like, I drew frame buffer 2. And so that's how like we would know that it's like okay to draw the next frame. But we are trying to do the stupidest, shittiest thing that we can do right now, right? And so to do that, we just say fuck this shit, and there's no way to do tear-free rendering. Fuck it. And we only support one frame. Fuck it. Okay, so I think I want this to like have like a null plane update here, and we'll use null plane update for the cursor. And then on the primary plane update, we will actually do some work. So I think it's going to be like, somehow we have to like extract information about like our GPU private structure, which I don't think we can here because our planes aren't like members of Sphero priv. So like I don't know how they do this in like vert IO GPU or display. They call like when they make their planes. How do they actually do work? They call here vgdev, which comes from dev private. So got it. So you go from plane to DRM device, from DRM device to implementation. So in ours, that means that we have to make sure that we have our device as our device accessible, and then here we can just go where the fuck we were. Plane dev. This is a DRM device. Yep. Then we have Sphero priv is a Sphero. I guess we'll call it priv, and he comes from DRM dev private data, which is a void star. Okay, and now we can just like start fucking writing shit, right? We could go like priv regs 1 is equal. I think that our regs are 32-bit. So we would do something like, I will write like address and and then we do like priv regs 2 is equal to address shifted right by 32 or something, right? Now this is assuming that we have one address available, but that is not true. That is not true. Oh, oops, I probably should have written down here. Time, that's fine. We don't have that. This is actually organized in RAM. Like, you have things that are like pages, right? So you have like 4K of RAM here, and then like another 4K over here somewhere, and then 4K over here. And these live like kind of like somewhere. Each page lives somewhere in like physical memory. And you program the memory management unit to kind of say, if I want these to look like contiguous sections in my process, you have like a process table that kind of has like the table mappings, right? So it goes like, oh, 1, 2, 3, 4 in virtual memory points to like 5, 6, 7, 8 in physical memory. But like, address 4000 points to like 100 or something, right? Like these can kind of like be mapped however. And these get like loaded on like context switch and stuff. So here we have like we've asked for our memory to be like laid out this way, I think. When we called like shum dev gem shmem create, this says like, hey, could you like take some shared memory and give it to us for use with like the Linux graphics systems stuff, right? But this thing allows you to kind of page memory however, because it's like way easier, right? Like that way, if you want to allocate a frame buffer that's like 4K, you don't need a 4K sized buffer. Well, not 4K is the wrong word here. 4K pixels across, so 4K times whatever, right? You don't need all of that memory in one spot. You can kind of like gather it from wherever in physical RAM it like actually fits. And so what they do somewhere is I think there's like scatter gather table something. So they say like, hey, let's get that memory and like collect it all up, and we will tell the PCI device where each page is, and it can like restitch them together. I believe. It would be nicer if we could just create it with like, it would be easier like for right now if you could ask it to create the memory kind of like all together. But I think that that's not worthwhile. Like that's probably not going to be simple. So I think we just kind of do what they expect. So I think in the vert.io stuff, we saw something that was like map. Where did we find this the other day? I think we came at it through like the QEMU source code. So let's go over here. Let's get into our QEMU development environment. And we can look for the command that is used to send that memory. I can't remember what it was, but I remember seeing something in like source QEMU, like something like vert.io GPU. I remember seeing something like Pixman. They create like a Pixman buffer here. Pixman image create bits from vert.io GPU resource create 2D. Yeah, so here we're looking for command resource create 2D. That's what we're looking for. So resource create 2D. Okay. Then there was something about like this creates the resource, but then someone else maps it. I think. This looks familiar. Something scatter, gather, table. We would have been when we were looking at like the frame buffer stuff. It's not really here. Not really here. I can't remember, man. That's bothering me. Where would we have seen it? Um. Dun 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 dun. Fence control buffer. Yeah, it wasn't really this. Oh, wait, this actually looks familiar. SG Unit 1. Transfer to host, submit, resource flush. Primary plane update? Yeah. So on primary plane update, they call set scan-out. No, and then they control the buffer. So somewhere, they must get the buffer object from somewhere. Buffer object, here. Okay. Then they must map the memory here. Hardware resource handle. Oh, they kind of map it before that. Right. So they did it on they did it on frame buffer add. That's, I'm pretty sure. Pretty sure. So kind of like here. Frame buffer create. Frame buffer init. Yep, this is looking familiar. Or maybe it was on buffer creation. I can't remember. It was like DOM. Create DOM and map DOM. So when they create the DOM buffer, did they do something funny there? They just called create. Yeah, so nothing here. Nothing here. So the frame buffer path does feel more likely. How do they... Fuck, man, we found it. We actually did find it. It was on like set CRTC maybe? Which would be in like... Maybe we go into like drivers, GPU, DRM, vert, IO. If we just like grep in here for like SGT type shit, or like DRM map pages, or like hold on, source Linux, drivers, DRM, GPU, DRM, vert IO. Okay, grep, like DMA. Okay. This feels like what I was looking for. Yeah. Yep. Okay. So here on plane update, they call transfer to host 2D, which just takes in this like buffer object here. Yes. And then here he says synchronize the given buffer for DMA. The device which performs the needed cache synchronization, it moves the ownership of the buffer back to DMA domain, so it is safe to perform DMA operation. I'm not 100% sure this is the only place though. I remember seeing something about like mapping. Map. I'm not 100% on this. Not 100%. Because this is only an update. Submit. Prime. Definitely not prime. That's not what we're looking for. Could be invert IO gem. Prime export. So does that line up if we look at transfer to host 2D, who DMA syncs this stuff? Oh wait, we saw somewhere there was like ents, and nents. Where does this come from? Object create. Yes. This was it. This is what I'm looking for. This is what I'm fucking looking for. Right. So when they created their shared memory, they immediately fucking send that shit. Send that shit at the PCI device. So here they create the resource and then they immediately attach data to the resource. This is what I was looking for. So in here, they had the entities came from like here, maybe? Yes. This is what I was looking for. So they call derb gem shmem get pages sgt. So this pins the pages, DMA maps them, and returns a scatter gather table for them. This is exactly what I was looking for. So this function returns a scatter gather table suitable for driver usage. If the scatter gather table doesn't exist, then the pages are pinned, DMA mapped, and an SG table is created. This is the main function for drivers to get at backing storage, and it hides the difference. And it hides a difference between DMA buff imported and natively allocated objects. Hell yes. Okay, so this is what we're looking for. This is what we're looking for. God damn, dude. I knew it shouldn't have been that hard. Okay. nvim cd source Linux. And we are looking for derv sphero derv here. So on our plain update, we want to call this thing. So this is going to come from what? Some sort of like shared memory handle, which I don't know where ours is, to be honest. Right, like our plane has to be attached to a frame buffer, I would assume, but we've never hooked up the plane to a frame buffer, which I guess is probably what prepare FB is for. Right? So like here, we're going to have to like extract frame buffer for our plane, map the pages, then write the pages. Okay, so here's what I'm going to assume for now. I'm going to assume that we can write out all of these pages at once, right? And I'm going to assume that if we write to these two registers, that it will trigger some action on the PCI device to write out that memory associated with this item. Okay? So I think that we can just kind of loop over, like, for each page in pages, essentially, do like this, right? As well as probably this, right? That's kind of what I'm assuming we can do. And then on the other side, we will see an address and a size, and we'll just like fucking rip that shit into a buffer, and we will assume that they go in some well-defined order, right? So we can kind of assume that like the pixels will probably come in like, you know, top first, like in order, right? That's what we'll hub. So we'll say for each write, we're kind of getting like the first n amount of stuff. Non-codes, thanks for the raid. What's up, everybody? Have to raid and leave. Hope you have a good stream. We sure will. Okay, thanks for the raid. Hello, new viewers. We are working on a GPU driver. So the idea here is that we are implementing a virtual GPU in a virtual machine, and we are writing the equivalent driver to go with it, just trying to get a picture of anything. So the goal for today is just if we got, a little picture of a smiley face rendered out somehow, that would be a huge win. And we're very close. We're kind of at the point where we have all of the memory in the correct location. We've kind of got them allocated through the driver subsystem in Linux, and now we're just trying to be like, okay, so how do we get this memory to the PCI device? And so we are kind of assuming that we have this guy is split up into bands of pages that might be kind of allocated just kind of anywhere in system memory. Right? So it's could be like this guy's here, this guy's here, and this guy's here, right? And so we're what is our interface to our PCI device in order to write that shit out? And so we were just kind of saying for now, we'll do the stupid thing where we're just going to write 3 registers with an address of physical memory, as well as the amount of stuff in that physical memory. And we just have to figure out how to get that shit, which I think is this. So what does this guy take? He's mad for some reason, so he's expecting a derm gem shmem object. So this, we don't know what that mapping is. I think that probably when somebody calls prepare frame buffer, I would think on our plane, and we must have to use that to link the plane to a buffer. That's kind of my guess. So let's see what is going on here. So this is Pharaoh GPU prepare FB. GPU plane prepare FB. And presumably in this state somewhere, they must have the frame buffer. Yes, very nice, very nice. And the frame buffer must have the actual data associated with him. Here. So we can be like new state plane frame buffer obj 0. So this is our object, and we need to associate that with the plane somehow. So can we just kind of is we have private data that we can work with here? Doesn't look like it. It looks like what we should do probably is kind of store this in our driver data. So here we'll say primary plane buffer object. The data associated with this thing. So this can just be a DRM gem object. Okay. So we have in our private data, we say struct DRM gem object. This probably needs to increment the reference count. Probably. And when we initialize this thing, we need to make sure he's initialized with 0. So we do 0 alloc this thing with KZ alloc. I believe the Z in Z stands for 0. Yes. So I think we're chillin'. So I think here this is null by default. And on frame buffer assignment, we can say this, I believe, increments the reference count. So we kind of take this, and we assign that into our state. So we need to get our state out. So it's kind of like this. We say priv primary plane buffer object is this. That sounds fine to me. He's kind of mad about something here. Assigning to struct. Oh, because this doesn't actually return anything. So we kind of do this instead, where we go, if we already had a buffer object, then we need to fucking free that shit. So gem object put. Then we assign this to be what is associated with this plane, I think. And then we immediately increment our reference count to that thing so that we don't lose it. Seems reasonable to me. Seems reasonable to me. Okay, so now we have a buffer object. So here we should say if does this if priv primary plain buffer object, if it's not available, we should like, can we do like a bug on? Yeah, let's do that. Crash our fucking kernel. That's a fucking bug, baby. That's a fucking bug. And he's mad here actually because he wants a derm gem shmem object, which is not what we have. We have a derm gem object. So how do we get the derm gem shmem object back? Derm gem shmem object. He has a derm gem object inside him. So we can go backwards from this. We know that if we have this thing, his pointer is inside some derm gem shmem object at base. This should be totally legal. So here we say the this thing shmem obj is equal to this. This container overturns a pointer, right? Yeah, I think so. So now we have like these this like table. Of like pages in memory that are associated with this thing. So probably before we do fucking anything here, before we try to communicate with the GPU at all, I think it makes sense to just look at what's inside here. We expect to see a lot of yellow for our little yellow smiley face that we're trying to draw. So I'd like to see like how do we iterate this thing. So we saw here, we can just call this. For each thing, I wonder what the difference between this DMA and not DMA API is. Because these are both physical APIs. I guess DMA addresses don't necessarily have to be something that you can access physically through your thing. They just have to be something that the other device can access. So there's probably something funny going on there that they kind of turned into the same thing. But then can we see like, you know, can we just look at like the address? Like, is that a thing we can look at? What is like the type of like pages and shit here? Pages, SG, and SI. Okay, so we'll just kind of copy these here for now. Hey all, hello, hello. And I just want to like look at this shit. Like, what is it? So this is our pages. Pages for us, we call it SG table. Okay, and so scatter list, is that our iterator? No, this is our current location. So we have page length, offset length, DMA address, DMA length, DMA flags. So we actually like might not really be able to look at this shit directly, which is kind of annoying. I kind of want to see what's in it. I want to just look at it. Is there like SG? Oh, it would just be so nice to look at. I guess we could go through, I mean, they had SG Fizz. Is there other like SG Vert? This is probably what I want. This just gives me like a fucking address I can look at, right? The caller must know the SG space and has a valid virtual mapping. Oh, I guess we don't really know that. Can we like map it? I just want to look. Okay, we'll ask the idiot. If I have a, what is it called? A fucking, struct sg table in the Linux kernel, preparing for DMA with a PCI card. Can I look at the contents of the memory I am about to DMA from the kernel? Is there an API for that? I see stuff along the lines of sgfizz and sgvirt, but am unsure the rules about how to use them. This guy, like, keep in mind, this guy's a fucking idiot. It might be wrong, but this function tree is corresponding to a given scatter gather. This is what uses access the memory kernel, so that lines up with my current understanding. So that's at least, you know, something. This is probably the piece I was missing here. So he gets the virtual address, and then he calls sync for CPU. That's really the piece I'm missing here. So this takes in a struct device. Why? What is the device for? Whose device is this? Okay. Is there like DRM sync? I mean, I guess we could maybe assume that it's related to... When did we create this thing? We called gem object somewhere. Create buffer. Dom create here. We called derm gem shmem create. Okay. So then this guy must make like a DMA-able thing somehow. I guess the device must be whoever he uses internally. In here, right? Like somewhere he must call a similar function. Obj dev dev. So this is drm gem object, drm device, base device. Okay. So we can probably assume that we can call like drm dev dev here. And then he's kind of saying you can just fucking run it then. So he has data as sgvirt sg. So we have just like uint8 void star data, I guess. Probably this returns. So we can call uint8 t star data. Okay, fuck it, right? Oops, where the fuck did I just go? There we go. U8 star, I guess, is probably like the kernel type for this. And can we just like fucking print that shit? So what's the size? What's the size here? Scatter list. DMA length would be my length probably. Length. So for zero, int I equals 0, I is less than sg length plus I. Can we just like print data? Probably in hex. Data plus I. I don't know. Print K. I'm down to fucking run it and see. I'm down to fucking run it. So what are we expecting to see? We're expecting to see a bunch of yellow. A bunch of yellow. He's mad because he wants to return somewhere at 224. Yeah, okay. Bounds check. Surely this has to be done. I'm so used to fucking Zig doing it for me. Okay. Run it. Quit it. GDB it. All right, let's fucking see it. Okay, so I kind of expected to see our function. Oh, continue. Okay, so I expected to see something happen there, which I don't, which is kind of weird. This prepare FB is just like somehow never called. So that's kind of weird. Well, I guess we can't be sure of that. We can't really be sure at this point. Maybe it's called and it just doesn't, our like loops have nothing in them. So here in DRM atomic helper prepare planes, we expect him to end up here. So let's kind of like breakpoint here. Can we delete breakpoint 1, continue, and then run our test app again? Okay. Yeah, okay, so he doesn't have anything there. So that's very surprising. Very surprising. Because because maybe cursor and primary. Do we register the primary? We do. Kind of want to see. It's weird that he only tries to run that one time. Oh no, he does try to run it twice. I just continue on the second one like a dumbass. Hold on. Run again. Continue. I don't really know what's happening right now. But now we're seeing something. Again, it's null? Oh, so we're probably seeing after the 5 seconds, he tries to prepare the frame buffer again on quit. So I thought that this prepare frame buffer would be called, and it is getting called, but for the wrong plane, which is kind of surprising. Pretty surprising, to be honest. So that would do it, huh? Where we were assigning the cursor helper functions to the primary plane by mistake because we were using the wrong variable, like fucking dumbasses. Like fucking dumbasses, man. Man, thank God that often like the code you write has observable effects, because I feel like my like workflow often is just like fuck it up and then like fix it later. And like I wonder how many bugs I write that I just like don't notice. All right. So now on prepare FB, he's got a null pointer dereference. That's kind of fun. That's kind of fun. So that's here. I wonder where. So we can check this here. So we'll set, I think we can go into our here, and we can say info line, and we just kind of ask it, where the fuck is this, man? Why is that not copy pasting? No? Do I shift click here? So this is at line 223. Right here. Right here. So which of these like many things is incorrect is the question. I guess we just breakpoint here. I don't know if it's going to let us run this again without like fucking falling over. It does look like the kernel just like hard crashed. So I guess we run it again. And this one's kind of tricky because the breakpoint we have to set is like inside this kernel module that he doesn't know the address of initially. So I don't really know how we're supposed to like automatically set up these breakpoints, to be honest. So I think we'll just have to do it manually because I don't know how to do it. I don't know how to do it. But I do know how to just do it manually, right? We run Control C, LX symbols, that will load LX symbols, break here, now that is available for us. Root test app, and let's look at priv primary plane BO. So that's fine. New state plane FB. So the new state plane FB doesn't have anything. So how are we supposed to do anything here? Vert IO, vert GPU display. How do they do it? Prepare. I guess we look for references to this, and we look for the one in vert GPU plane. I guess we just do this. I guess it's like a thing that can happen. Should we read the docs? Let's look at prepare frame buffer for scan out by pinning its backing storage or reallocating into a contiguous block of VRAM. Other possible preparatory work includes flushing caches. This function must not block for outstanding rendering since it is called in the context of the atomic octal in for async blah 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 blah. This persists after the end of the atomic commit. Resources that can be released at the end of commit, blah, blah, blah. Okay. I mean, I guess that's fine, but it's kind of confusing to me why this is happening. Makes me think that my understanding of like when this is called is not correct. But, you know, I guess we just fucking run it. And we'll maybe print K, no plane frame buffer. And then we say got plane frame buffer, because I kind of want to see if this ever happens. Because it's kind of confusing to me that it's not. Kind of confusing. Because otherwise, I have no idea how I'm supposed to trace that shit together. Okay. Like, how are we supposed to tie the buffer to the plane? I don't know. I don't know. I thought it was here. Okay, so here, no plane FB, and then we bug on 192. Right, so then we don't have a buffer object available. So, like, what the fuck? I mean, it could be called that this is somehow called multiple times. Could be. Because what does he do here? If there's no frame buffer, he goes, okay, I'm outie. Then he says, if there's no buffer time, or we're a thing and no thing, okay. Yeah, I mean, I guess it doesn't do jack shit out here, huh? Atomic update? Where does he get his buffer object from? So there might not be a handle here. There might not be. Which is kind of surprising. Kind of surprising. But I guess we'll just play the same game. I guess we just play the same game here. And we see where it goes. Maybe they call multiple times. Print K, no plane buffer to update. Right, we're just gonna get the fuck out of here. We'll just see what happens. Run with GDB, continue. Let's just see where we go. Let's just see what's up. Yeah, so he just says no plain frame buffer, and no plain frame buffer to update. So right, so we just never tie the frame buffer to the plane, which is surprising. I wonder if we're supposed to do this on like add frame buffer call. I wonder if we're just supposed to kind of like assume that that's like tied together. I guess this stuff could be relevant. Probably, right? Surely, maybe it could go here. So in our little test app, we say, hey, I have this CRTC and this frame buffer that I'd like to tie together. So that kind of feels like it's kind of should go in here somewhere. So we can look at the usage of this in vert GPU. And in one of these many things, does he... I mean, this kind of feels like where it's supposed to go. Can we look at this? So, after mode set, I guess we just look at the implementation. Like, where's like atomic DRMI octal? That's probably where it makes most sense. I'd imagine display drivers are hard to test, at least on real hardware. Am I right? I don't know. I've never done it. Set CRTC. So this is the call that we think should like actually trigger something to like show up on the screen. So what I want to know is like one of the many things that we pass into this. One of the things we pass in is like the frame buffer ID, right? That's what we passed in here. File priv void start data. Data, here we go. This is the request. So who uses this shit? So there's some like frame buffer ID lookup in here. So we can just look for like okay, so he gets this frame buffer. We should check that we end up here. Can I put a comment here that's like frame buffer lookup? Then surely like somewhere he like uses this somehow. Set.fb equals fb. Okay. Set config, which we have set up here. This goes through to like the DRM atomic helper. And set FB for plane. Okay, wait, this is exactly what I'm looking for. So this calls DRM frame buffer assign plain state FB. Maybe we should turn on these DRM debug logs and see if they tell us anything. Because it sounds like to me that the DRM plain state should get the frame buffer assigned to it, like I thought, right? That's what I thought was going to happen. But like something here is not doing what I expect. So it could be like order of operations here. Could be. And then he calls update output state. So like set CRTC for connector. Surely this is going to end up somewhere in our like set CRTC somewhere. Yeah, I'd like to turn on these debug flags. So I think that this was in sys module DRM parameters. We could echo userspace to debug to turn on all debugging things. And we can just run our test app again. Okay. And we could just kind of scroll back in this shit and try to see if we see anything interesting. So, like, for example, we're looking for set noFB for plane. Or like set noFB for plane. Okay. So like why? That means that this frame buffer is not initialized at this point. Right, so we're kind of on the right track. It's that this set of B either equals null here. Okay, it could be this. Or it could, which is means set.mode, or we had like here. Okay, this is the interesting piece here. So we should set a breakpoint here and look at the contents of set. I think these are the next two pieces to look at. Okay. So here, we did get a frame buffer out of that. So that's a really good sign. With like a 1024 by 768. So that looks a lot like we populated this what we wanted it to be. But can we look at like set here now? So we have mode, we have FB. So neither of these two things seem too suspicious to me, which makes me want to step in here and try to figure out what the fuck is going on here. Right, because we saw that he was in no FB mode. Is this vendor specific? Some of it is, some of it is not. So the code we're in, like at this very second looking at, this is kind of like DRM subsystem helpers that we have like kind of opted into as like our vendor Spheriphoria. But we, sorry, my brain. There's also like vendor specific code that this is eventually ending up in. Because we assign like this, the generic subsystem has like helpers, and those helpers are ours. So I think we just fucking breakpoint it here. Which I think we might already have. Info BR. We have one at, no, let's just set one here as well. Okay, continue. So this is where we were seeing that no FB log, right? So here we should see FB here. Oh, he is set. So how come in our logs we didn't see like set FB for? I guess it's gone. Okay, wait, that kind of makes sense then. So we're missing something. We're definitely missing something because in here we definitely ended up in the path where he logs set FB for plane. Okay, so let's try to look for that. Then we also see a state where we're in set no FB for plane, but that's when the process ends. Okay. Sys module parameters. Sorry, DRM parameters. Echo userspace to debug. Run it again. Yep. So we should go through here. And we should see a set of B here. So it would be in here somewhere. I just have to find it. Am I stupid? Can I search in this? I guess I can copy paste it out. Copy? No. I guess we copy with the middle click buffer. Here. Set FB for plane. Okay, so we do see this. We do see this. That's a good sign. That's a good sign. Oh, and even here, we see print new state. We see plane 34 has frame buffer here allocated by test app with this size and shit. So like, what's the fucking problem? What's the fucking problem? Because down we get to here on commit, it's fucking gonzo, right? So somewhere between here and here, something has gone wrong. Print new state, checking F1A93FE, which is again here. So committing this, right? He commits this. This is the same fucking buffer, right? He's committing this here and he's going, whoa, no plane FB. So somewhere between here and here, we've lost it. We've lost our frame buffer. Or we're doing something fucking stupid. That's also like a very real possibility, right? That we should always keep in mind. So let's look again at our no plane FB. This is kind of where it falls over. And so maybe we should just kind of set a breakpoint in here and backtrace and try to figure out where this thing should have got set. Maybe new state isn't what we think it is, right? Maybe it's actually under plain state. Could be, right? So let's set a breakpoint here. And we can do LX symbols. Except I spelled symbols wrong, so it's just gonna like fucking freak out at me. Oh, I guess I have to pause the app. Breakpoint here. Okay, continue. And luckily I think that like nothing's crashed to the point where we can't run again. So can we look at new state plane FB? Okay, so he's mad. But what about if we look at plane FB? Also null. Okay, so somebody has gotten angry between then and now. Now if we look at like the current debug output, we see that he did print that there was supposed to be something there. So what the fuck happened? Let's look at the backtrace. Okay. So we're at atomic commit. Okay, can we look at like... So we're calling prepare FB with plane and new plane state. Where new plane state comes from 2601 in atomic helper. Okay. New plane state. So this is for each new plane in state, okay? Okay. So what's our thing? State? Optimize out? Fuck. I wonder if we've like somehow like mismatched our cursor and primary planes again. That's a very like likely place where we would have fucked up. Very likely fuck up place. So this comes from primary helper functs, which are attached to the primary plane, who has type plane primary, and we have the cursor plane helper functs do jack shit, okay? Who are attached to the cursor plane. Cursor plane is used here, 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 Primary plane should be used up here. Great. And then is it possible that we've switched the order of them in the init with planes? No, they go primary then cursor. So I don't really see anything crazy there. I really don't. I guess if the format was rejected, that's a possibility. What are we trying to do in our application? Do we ever like try to set a specific like buffer color type somewhere? Create dumb buffer. And then we add a frame buffer with bits per pixel 24. So I don't think that's a problem. When we make our frame buffer, here, frame helper check. Somewhere we do like, we check for if something is 32. Here, dumb create. Oh yeah, okay. Should be fine. Should be fine. Does it check for all new plane state? Does it error out on the first where it's wrong? Good question. Good question. So this is in here. He does fail out on the first prepare FB. So it could be if we're like looking at the cursor one first. But like here our prepare FB doesn't fail. But I would be interested in maybe looking at like my multiple frame buffers in here. So I'd be kind of interested in breakpointing on this. And kind of seeing what that does. Let's just give him a sec. Give him a sec. Okay. Test app. So here, can we look at like state? Optimized out? Fuck off, man. Oh, it's so fucking annoying. Okay, so like funcs here comes from plain helper private, and plain is iterated from planes I dot pointer. Fuck off. Fuck off. But I guess if we go up a level, we should be able to look at the state here. Yes, okay. So state, what are my new plane states in here? It's state arrow planes. 0 and 1. Okay, planes. Can I look for like? He's going for I. How does he like bounds check this thing? For each if planes pointer. So it's kind of like null terminated. It's null terminated. So we have one plane here, and then the second plane is null terminating. Okay. So planes 0. Shouldn't we have multiple planes? Like the cursor plane and the primary plane? Maybe not. Maybe the cursor plane's not used here. Maybe the cursor plane's not used here. Oh, apologies for the lag. Apologies. Okay, so there's only one plane. And we have state. Okay, wait, plane 0 state FB does exist. Okay. Okay. That's a good clue. Which kind of makes me feel like in our function, we should see plane state FB, which is 0. So what am I missing here? What am I missing here? Where this comes from new plane state. Oh, okay, wait, hold on. So we have this guy has a frame buffer. But if we look at the new state, that also exists. But old state does not. So this guy is supposed to say, hey, I'm looking at the new state for each of these things. New plane state is equal to this. And as far as I can tell, at least at this call site, at DRM atomic helper prepare planes, this is fine. But by the time we get into our call down below, it's not fine. So DRM atomic helper commit. I guess we kind of know exactly what line that's supposed to be at. So this is at atomic helper 2029. So at this point, he thinks it's fine. And then that's literally like one level up. So like, what in the actual fuck? What's our I value? 0. Dude, I'm actually gonna lose my mind. New plane state comes from state planes I dot new state. State has been optimized out. Which is valid. What the fuck? I mean, this could be some like GDB shit. Could be, right? Very well could be. But the way that this is like really what I would expect, right, is very confusing to me. Very confusing to me. And what's even more confusing to me is there's nowhere between these two places that like I expect to see like something change. You know? But like, sure, I mean, for sure in here. Oh, fuck, fine. Oh, wait. Am I stupid? Oh, new state plane FB. But there's new state FB. Do I just have to attach? Have I been like looking at the wrong fucking thing? Hold on. Maybe here I'm supposed to set that. Okay, wait, hold on. Now I'm confused. DRM plane. So there's new state FB and new state plane FB. And new state FB must be what is propagated on from that set CRTC thing. Okay, I think I'm understanding, at least a little bit. Right, because they have mode CRTC. This is the frame buffer ID that we're trying to render. Which we extract from this thing. Which we then apply to set FB here. Okay. And yeah, of course the plane doesn't have anything. So this is where it's set. I was confused all the way around. So now the question becomes, is it expected for me, the driver writer, to just fucking send that shit? Or is that like internal tracking? So I would love to see DRM plane. Currently bound frame buffer. Do not write this directly. Use DRM atomic set FB for plane. Oh, yes. Okay. DRM atomic set FB for plane. Who the fuck calls this? Some people in here. Ah, wait. Okay. So this comes from set arrow FB in like DRM atomic helper set config. Primary state. Set FB for plane. I forget. Did we not see this though? This looks familiar. This looks really familiar. But I don't remember. Okay, I want to go down here now and look at this set FB for plane then. Because I remember this frame buffer being null, actually. That's actually what I remember. Okay, so we're in set FB for plane here. Which comes from set config on set CRTC, right? And this is valid. Okay. So this feels like he calls DRM frame buffer assign here. Okay. And at this point, we should see primary state plane FB 0. What the fuck just happened? Right? Because we just saw set FB. This is valid. Oh, this is also valid. This comes from plane state. Oh yeah, primary state FB is set here. Okay, wait, that's good. That's good. So I feel like this is what we want, right? Our primary state is a DRM plane state. So who... Which comes from the CRTC primary, okay. So we are seeing a plane get a frame buffer associated with them. It's just not the plane that we're seeing. For whatever fucking reason. Can we look at like this? Who uses... Oh. I think I'm confused about levels of stuff again. Because when we get this in, we get a DRM plane input here. And a DRM plane state. Back pointer to the plane. So I'm confused here. Maybe we're just not ever supposed to look at this. Like, is this just supposed to be like this? And then this might be like the old, this might have like the back pointer might be like the old plane here. And we're like switching them out or something. Maybe. So if I call prepare FB here, this one is to prepare a frame buffer for scan out, e.g. by pinning its backing storage or relocating it to a contiguous block of VRAM. Other possible preparatory work includes flushing caches. This function must not block for outstanding rendering, blah, blah, blah. Okay. Okay, I guess that's kind of reasonable, I guess. So we then just kind of attach the wrong thing. And then in this function, we could have checked. It actually turns out we probably could have just checked. We probably didn't need to do this, actually. Actually, we break here. Can we look at the plane that we are committing? He doesn't have a frame buffer. Maybe that's because he gets set after our function finishes. So this is kind of weird here. So the new state here. Yeah, there's something odd here that I don't understand. But we have the state here. So I guess we could have been looking at a state planes 0 pointer FB, right? No, even that's not okay. So how come he was in the new state here, but he's not available to us on the plane update here? You know? CRTC, like... new state, maybe? Oh, yeah, wait, am I supposed to look at P state, planes, 0, new state, FB? Ah! I see. I'm supposed to be looking at the new planes. So I think we just don't need this prepare frame buffer thing. And in atomic update, we can in fact just extract the information that we want here. So it's this. So it's just boom, state. How am I supposed to know which plane this is? Current atomic state. Is there like new state for this plane available to me here somewhere? I guess I'd also look at plane state. Plane state. No symbol plane. Plate. Plane state. FB. Okay. So I look at this, which is about to be committed. This is what I'm looking for. And then fix me. Does this need, am I mutex locked right now? I'm not sure. But we fucking finally found it, guys. We fucking finally found it. We found our frame buffer. It took about like a fucking year, but we got there. Okay, so we have this thing now. And we can extract the buffer object from this. Okay. So that means this primary plane buffer object goes away. And this is a struct DRM gem object. And Then we get the shmem object out of this gem object. Okay. 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 And then maybe this works now. Let's fucking hope. It'd be so cool to see something that was like sane. Some real things that I wanted to look at. Some yellow. If it's yellow, let it mellow. I sure hope that we can be mellow now. Also, I think that you should flush your pee. It smells really gross if you don't. I assume everybody's pee smells gross if you don't, but like maybe it's just my pee. But I would like to hope that it's everybody's pee. Otherwise, there's something wrong with mine. That looks some like fucking yellow, man, if I've ever seen it. Now, that's a lot of printing, but we are seeing like alternating FFs and zeros. So I think that what will be an easier test here is we can count how many yellow pixels and how many black pixels we see, and how many other pixels, and we can check if that matches our like assumption about what a yellow smiley face should look like, right? Because the image that we're rendering is something that looks like this. I think you need to see a doctor. I think you're fucking with me. There's no way that your pee doesn't smell bad if you leave it in the toilet for a long time. It's gotta smell bad. I think that you have to, that's why you flush it. Right? So we should see like, this should all be like yellow. And this should be black. And we should see nothing else. How long are we talking? I don't know. Like, if you only ever flush the toilet when it wasn't yellow, then like you'd be leaving it for like 24 hours, right? And that would smell disgusting, I assume. I mean, I could also just be wrong here. Maybe my pee smells great after 24 hours. I'm just kind of making an assumption that would smell bad. I'm just making a big assumption, I guess. So count yellow is 0. We'll do this. And count black, also 0. An hour in the summer is too long, flush it. Okay, at least you have one guy who agrees with me. I can leave it for 4 to 6 hours and it doesn't smell bad. That's crazy. I guess in your world, if it's yellow, you can let it mellow. Even if it's yellow, not if it's just clear. I can see if you've just got like well hydrated peas, it would be okay. But yellow pea, I think that stuff's gotta start smelling bad. Okay. So instead of printing here, we're going to check. I think we're going to iterate this as U32s. And we're going to say, for I is 0 to length over 4, let's try to count how many pixels we see. So if we were going to say, let's look at our example app again. So our example app writes out. He clears it with FFs are in the middle. FFs are in the middle. So we go, if data I is equal to 0x FF, or 0, 0, FF, FF, 0, 0, oh jeez, I've actually flushed and gone away for the weekend. That would suck, coming home to just like, oh, that's gross, that's gross. Let's change topics. We don't have to talk about this. This was my bad. This is my bad. Else, if it's black, let it smack. Count black goes up by 1. And otherwise, we have count other. And we should set our count other also to 0. Okay. Then we will say print k yellow this many, black this many, other this many, and we're hoping to see a lot, a little, none, approximately. If it comes out black, definitely go see a doctor. Dude, black is crazy. Red's like, oh god, scary, go see a doctor. But black is like, what is happening? Like, I'm drinking tar. Stop drinking tar. All right. All right. View, serial. And continue. Oh, let's fucking go, dude. It took us like fucking forever. We also page faulted somewhere later that we have to think about. But we do see we finally we walked all of the pages associated with our virtual memory for our yellow face. And we do see yellow, black, other. That looks like a face. That looks like a face. Now we could also check maybe how many pages we're walking. Just to make sure that we're actually doing something that I think we're doing. So we'll say num pages plus 1 here. And that's pretty sick. I really wish we had something more visual to show. But this is pretty cool. Pretty cool. Serial. All right. One more time. All right, let's see it. Oh, we didn't log the number of pages. Fuck. One more time again. This time's the real one more time. Could be really bad blood. Ew. I don't like it. All right, let's see. Let's see. Test app. Yeah, so we go over 220 pages. But we do see that we see consistent stuff. So that's really good. That's really good. That really indicates that like our expectations of the memory layout are correct, right? We're seeing like, you know, a yellow page over here, and then like a yellow page over here, and then like occasionally we'll see like a page that has like yellow with some like black in the middle or something. Which is pretty sick. Pretty sick. Okay, so it's 5:10. We've been talking about P way too much. So I think that is a good indicator that we've gone way longer than we should have. So I think we call it there. We've gotten, I think, to the point now where the driver itself is kind of doing what is expected of it. He's not actually talking to the hardware, but we have the whole flow of information now to the point where we are seeing the buffer that we are trying to write, the buffer that we wrote from userspace is in fact getting into the kernel in the right spot, at the right time with the right size and stuff. So I think that we're almost there. The only thing that we have left to do is to hook it up to the hardware. So I think that is going to be the plan for tomorrow. Is we're going to try to like map this stuff through PCI into the host. We'll try to write an image, and then we'll maybe try to integrate with QEMU's display systems. And then maybe if we get that all working quickly, then we can do like multi-frame stuff. But I think I'm very, very happy with the progress today. I apologize that it's not super visual. I was kind of hoping that we would get to something a little more visual today, but you know, we'll live. So thank you for watching, you guys. If you like what you saw, we stream most days at around 12:30 Pacific time to 4 o'clock Pacific time. It is 5 o'clock Pacific time now, so anywhere between 4.5 hours ago and an hour ago is when you should typically expect to see me. If you're watching on Twitch and you haven't been around much before, there's a YouTube link in the Twitch description where you can check out all of our previous projects. We're working on demystifying the Linux graphics stack right now, but there's a lot of other stuff if you want to check that out. QR code decoder, operating system, like some like 3D work in this one. You know, there's stuff in there. Maps stuff people seem to like. So if you want to check that out, there's Whale running terminal emulator. Also, GitHub link in the description where this will eventually end up under the GPU testing env, but probably not until I'm happy with like the current, until I can call it like a feature, you know? If you're watching on YouTube, there's a Twitch link in the YouTube description. Swing by, say hi if you feel like it. Drop your Twitch primes, like, subscribe. I guess if you want to see the 12:30 to 2 segment archived, those are archived in Patreon and YouTube member streams. So if you want to check those out, those are also available. And I think that is all we have to plug. Thank you for watching. YouTube, let's get out of here, and Twitch, let's find someone to raid.